Welcome to the Velocity and Speed Foundation Trilogy questions and model answers. Question 1. A high-speed train accelerates at a constant rate in a straight line. The velocity of the train increases from 30 meters per second to 42 meters per second in 60 seconds. Calculate the change in velocity of the train. So if it starts at 30 and finishes at 42, we need to find the difference between those two numbers. So what you need to do is take away 30 from 42. So 40 minus 30 gives us an answer of 12 meters per second. So final answer is going to be 12 meters per second. Second part of the question, use the equation in the box to calculate the acceleration of the train. Acceleration is equal to the change in velocity divided by time taken for that change. So in the last question, we've already worked out what our change in the velocity is. It's 12. So acceleration is equal to 12 divided by, now looking at the top of the question, we see that the time taken is 60 seconds. So that's why I've divided 12 by 60 here. That gives us an answer of 0.2, and then underneath the equation it says show clearly how you can work this out. So we've done that, but choose the unit from the list below. Now the units of acceleration are meters per second squared. So finally in the answer for acceleration, what we're going to write is 0.2 meters per second, and don't forget it's squared. Okay, pause the videos here, so I move down. These answers will be removed. Part B, which one of the graphs, A, B or C, show how the velocity of the train changes as it accelerates? Okay, I'm going to go back to the top of the question. So it's accelerating, but it's accelerating at a constant rate here. So that means its velocity should be increasing by the same amount at each point. Scroll back down to the question. A, we don't see any change in velocity, so it can't be A. B, it does say start at a velocity, it ends at a higher velocity, and it's a straight line, which shows us that it's increasing velocity at a constant rate. So B is the correct answer, and we're going to write B in the box provided. Pause the video here as I'm about to move down and the answers will come off the screen. Question 2. Figure 1 shows the horizontal force acting on a moving bicycle and cyclist. A is pointing in the direction the cyclist is moving, B is pointing the way back. What causes force A? Is it friction, gravity, or weight? So it's between the tyre and the ground, and it's friction which causes that force. Friction between the tyre and the ground is what propels the bike forward. What causes force B? So as I said, B is acting in the opposite direction. It's trying to slow down the cyclist as he's moving forward. That force responsible for trying to slow us down on our bikes, air resistance. Force B is air resistance. Part B, the cyclist used the brakes to slow down to a stop and stop the bicycle. A constant braking force of 140 newtons stopped the bicycle at a distance of 24 meters. It's going to underline some important information. Calculate the work done by the braking force to stop the bicycle. Give the unit. So I'm going to box the command word calculate. Every time we see calculate, it means that we're going to need to use an equation. And what equation do we want? We want an equation that has work done, force, and distance. So the equation is work done is equal to force times by distance. We have a force of 140 newtons and the distance 24 meters, so we times 140 by 24. This gives us an answer of 3,360 But what are the units? The question asks us to give the units. Now work done, or work, is the same as energy, okay? That means that energy and work both have the same units. So work done is measured in joules, just as energy is, and so the final answer is 3,360 joules. Question 3. A car and a bicycle are travelling along a straight road. They have stopped at roadworks. The graph shows how the velocity of the car changes after the sign is changed to go. So we can see on the y-axis we've got velocity in meters per second, and on the x we've got the time. Between which 2 points on the graph is the car moving at a constant velocity? Okay, so at the start, between K and L, it's at 0 velocity, so it's not moving, but it is at a constant velocity, but it's not moving. The question wants us to find when is the car moving at a constant velocity. And so looking to M and N, we can see that here the velocity doesn't change. It stays level, but it is moving, so it's at a constant velocity between M and N. Between which 2 points on the graph is the car accelerating? So if it's accelerating, it means its velocity must be changing. Now, in between L and M, we see it increases from 0 all the way up to what looks like about 12.5 meters per second. So between L and M, we can say that the car is accelerating. I've just noticed that I've missed out part BII from question 2. So pause the video here, get these answers down. I'm going to go back to that question and then move back to question 3. Okay, so complete the following sentence. This is question 2. II. When the brakes are used, the bicycle slows down. The kinetic energy of the bicycle decreases. At the same time, the something of the brakes increases. The temperature of the brakes, or the thermal energy of the brakes, increases. Okay, and now back to question 3, and it's the last part, C. So part C. Between the sign changing to go and the car starting to move, there is a time delay. This is called the reaction time. What is the reaction time of the car driver? So we've got to pay attention to this segment here of the graph. The point at which the velocity starts to increase is when the reaction time, this tells you the reaction time. As each small division is worth 0.2 seconds, that tells us that it takes 0.8 seconds for the driver to react. Pause the video here whilst I go on to the last question. Final question. Which one of the following could increase the reaction time of the car driver? Tick the box. Drinking alcohol, wet roads, worn car brakes. So increasing the time means that the driver is not be able to react as fast as normal. So alcohol is going to be the correct answer. It's going to increase the reaction time. The cyclist starts to move at the same time as the car for the first 2 seconds. The cyclist's acceleration is constant and is greater than the car. Draw a line on the graph to show how the velocity of the cyclist might change during the first 2 seconds of its motion. So the cyclist is still going to start after about 0.8 seconds because it's reaction time, but it could probably start a little bit quicker than the car just because it hasn't got enough mass or as much mass as the car to get moving. So I've drawn it steeper than the line for the car at this moment. And this is the end of the answers. Thank you.